Today we are going over improper integrals, and the basic terminology we would want to know is that divergent means it doesn't exist, and convergent means it can exist. This is normally determined by the outcome of our answer on whether it's infinity or negative infinity, which it doesn't exist, so that would be divergent. And the way I would like to remember that is that there's a D in divergent for doesn't, and then any finite real number, such as for example 5, is convergent, which can exist, which you can determine by the C in convergent. And so that's how I like to remember them. Now, there are a few types of improper integrals that I want to go over, which are infinite limits of integration. So for example, in our integrand, our bounds can be from A to infinity, or it could go from infinity to B. So this is the example given. And then there's also a discontinuous integrand where it goes from A to B, but for example, we're given a fraction 1 over x minus 3. So 3 cannot be an answer in that case because you can't have a denominator of 0, which doesn't exist. So you're going to have to change up your bounds. And in this case, we would have to change it from 0 to 3, as well as 3 to 5, which as you can see, I just replaced the B bound over here, and then I just replaced the A bound over here for this integrand. I just split it up into 2, but I will get more specific into how that works in the video. So let's begin our first problem. So our first problem is going to be the integral of x over x squared plus 1 squared bounded from 0 to infinity. Now the first thing you want to do is write this improper integral into a limit. So all you do is just replace this infinity sign with any variable, and I'll choose t, and we can set our limit to approach the infinity instead. And then the inside of the integral stays the same, which we can just further evaluate using u substitution, making our u x squared plus 1, so we can cancel out the x on the numerator, making our derivative 2x dx, and then making our dx equal to du over 2x. And assuming y'all know how to do u substitution, we'll take out the 1/2 and set it to 1 over u squared, which will then integrate to negative 1 over 2u plus c. And then we can substitute back our u. We can then set up the definite form of this integral, but let's first put our limit outside of it and then put our result inside a box, and then bound it from 0 to t. We then get limit t approaching infinity, negative 1 over 2 t squared plus 1 minus negative 1 over 2 times 0 plus 1. We can then just simplify it to the limit t approaches infinity times negative 1 over 2 t squared plus 1 plus 1/2, because a negative and a negative make a plus. And how I like to look at this limit is t equals infinity. So when we set t equal to infinity, which is basically 0 at that point. So then this just ends up becoming positive 1/2. And you could add the 0 in front if it helps, but overall, the answer is 1/2. Now, based on our definitions over here, would this be considered convergent or divergent? Now, since this is neither a negative infinity nor an infinity, and this is in fact a finite real number, this will be considered convergent. So our final answer will be 1/2, convergent. And we just solved our first improper integral. I would now like you to do this second problem on your own. So this may look like a simple u substitution problem, but it isn't. And the reason is because of this 0. If we were to set our sine of x to 0, our denominator would have a 0, and a cosine divided by 0 does not exist. So therefore, this is actually an improper integral. So in comparison to our first problem, we had an infinity sign in our integrand, making it fairly obvious that it was improper, but over here it's improper because of the dividing by 0. So let's just take our limit as t approaches 0 from the right. And determining approaching from the left or the right just depends on the other bound, and since we are approaching towards this pi over 2, it is going towards a positive area. So from 0 to pi over 2, you would use positive numbers to get to pi over 2. So we can write the integrand as cosine of x over sine squared x dx, sorry, that's a train, from t to pi over 2. So for now, we could just ignore this limit, but we will get back to it. So let's just evaluate the integral itself, which again, assuming you know how to do a u substitution, I will just skip all the steps to end up getting negative 1 over sine of x plus c. We can then go back to this limit as t approaches 0 from the right and put in brackets our 1 over sine of x from t to pi over 2, which simply gets us negative 1 over sine times pi over 2 minus negative 1 over sine t, which again all goes in coordination with this limit of t approaching 0 from the right, and our box just simplifies to negative 1 plus 1 over sine of t, again under our limit, which then plugging this t for infinity just gets us negative 1 plus infinity, which of course is infinity. So because our answer is infinity, with this conversion converge or diverge? Well, looking back at our definition, negative infinity or infinity does not exist. And because it does not exist, which starts with the letter D, doesn't, it will be divergent. And again, if it can exist, it would be convergent due to it starting with C. So our final answer is infinity divergent. Our third and last problem is going to be the integral of 1 over x minus 2 bounded from 1 to 3 dx. Now in our denominator, our x cannot equal 2, so it is discontinuous at 2. But in our bounds, 2 is not shown. But then you begin to realize 2 is in between those bounds, so what you can do is just split it up by putting the bound from 1 to 2 and adding it to an integral whose bound is from 2 to 3. And if you notice, it's still bounding from 1 to 3. All we did was split it up and the 2 is in between. So I guess if you're having a hard time seeing how that works, you could just put it like this and notice that it's going from 1 to 2 and then 2 to 3. But anyways, let's just see how that looks when we actually put it in integral form. And there we go, we split the integral. Now you're going to want to set a limit for each one, where for the first half of the split integral, our limit can be t approaching 2 from the left, because we're going from 1 to 2, which is from left to right. And we can have our other half of the integral go from limit of t to 2 from the right, because it's going from 2 to 3, which is going from 2 to the right, because it's going up by 1. So here our 2 was going down to 1, and then here our 2 is going up by 1, if that's how you want to remember it. So now we could substitute the 2 on each one for t, which in turn just gets you this. And from here, you would just do a basic u substitution to actually find the integral, which is the natural logarithm of the absolute value of x minus 2, and then bound it from 1 to t, which is testing this first half of the integral. And don't forget our limit, which then equals the limit of t approaching 2 from the left, natural logarithm t minus 2 minus the natural logarithm of the absolute value of 1 minus 2. And once you plug in our 2 over here into t from our limit, you end up getting negative infinity as a whole. Now, this saves us a lot of time if we find out that one of them doesn't exist, which clearly one half of the integral doesn't exist, it's the first half. And if you solve the second half, it also won't exist. But since one part doesn't exist, this overall will diverge. You don't have to test both, you can only just test one if one of them diverge. Now, if one of them converge, make sure that you test the other one just to make sure it doesn't diverge. But yeah, that is our lesson on improper integrals. Thank you for watching. Today's video is going to go over arc length, and I believe this is a nice break from all the integration techniques that we've been trying to learn and memorize, because it's fairly simple in comparison to like trigonometric substitution. And the closest thing to any previous lesson we've had with arc length, in my opinion, is disk and washer method, because it's basically just memorizing a formula and plugging it in. But in this case, I feel like it's a lot easier because it's a pretty straightforward formula, where our length is equal to the integral of the square root of 1 plus dy over dx squared from a to b dx. And this dy over dx is just an expanded way of just saying y prime, or the derivative of the y function as given here. So basically, once you find your derivative, you just plug it into this parentheses. And just like disk and washer method, it's dependent on what bounds you're given. So you can also have an x equals g of y instead of a y equals f of x, depending on what variables you're given. And I will demonstrate both here. And if you're curious as to what arc length is, it's basically just getting 2 points on a curve. And over here, I just drew a sun. So 2 points of a curve, like over here and here, and here and here, and just finding the distance between the 2 points. So our first problem will be to find the arc length of y equals 1/3 times x to the 3 halves, given the bounds x equals 0 and x equals 4. So your first step is just going to be finding the derivative of your y, which is just 1/2 x to the 1/2. And again, all I did was take the derivative of the y equals function, which is 1/3 x 3/2, and then plug all of our information into our first formula, because we are given y equals, as well as our bounds being in terms of x. So plugging in gets us L equals the integral of 1 plus 1/2 x to the 1/2, all under a square root dx. And don't forget to square our dy over dx, bounded from 0 to 4. Now when we simplify, we get integral from 0 to 4 of 1 plus x over 4 dx. From here, you could perform a simple u substitution, where we could set our u to equal 1 plus x over 4, which makes our du just 1/4 dx, which then makes our dx equal to 4 du. Now never forget about our u substitution rules, where our bounds will change in accordance to u. So our lower bound becomes 1, and our upper bound becomes 2. And now we just have the square root of u times 4 du. And again, all I did was just plug in these terms into our integral. We can then take out our 4 and rewrite this square root of u as u to the 1/2, which finally gets us 4 times 2/3 u to the 3/2 bounded by 1 to 2. And you can take out this 2/3, making this 8/3 times u to the 3/2 bounded from 1 to 2. And this definite integral becomes fairly easy, which gets us 8/3 times 2 to the 3/2 minus 1 to the 3/2, which simplified leaves our final answer to be 8/3 times 2 times the square root of 2 minus 1. And that was problem 1. I would now like you to do this second one on your own. Now, if you're intimidated by this inequality, don't. This is the equivalent of just saying our bounds are y equals 1 and y equals 2. And notice that all of our terms are in y, so we are going to be using this formula. So the easiest way to approach this is just to solve for the inside of the square root, but to do that, we also need to solve our dx of dy. And again, the equivalent of dx over dy is just finding the derivative of our x function, which is this whole thing. Now, once you finish deriving this entire equation, all you end up getting is y minus 1 over 4y, which is our dx over dy. So now we have something to plug in there, giving us y squared minus 1/2 plus 1 over 16y squared. Now again, this is just our inner function inside the parentheses over here because we squared it. So now we have to add this 1 over here. So 1 plus, and then this inner function, which simply gets us y squared plus 1/2 plus 1 over 16y squared. Now to make things simple, you have to recognize that this is a perfect square because this is equivalent to y plus 1 over 4y times y plus 1 over 4y. So if you merge those together, you get y plus 1 over 4y squared. And again, this entire thing solved for the inside of the square root over here, which has so many arrows. So bringing this back down, we could pretend like we're plugging this guy in here, which gets us L equals the integral of the square root of y plus 1 over 4y squared. And remember, our bounds are equal to y equals 1 and y equals 2, which is our lower and upper, so 1 to 2. And of course, the square root and the square cancel each other out, so we're left with L equals the integral of y plus 1 over 4y bounded from 1 to 2 dy. Now we can evaluate each integral, with our first part being y squared over 2 bounded from 1 to 2, and then the second part, which is 1/4 times the natural logarithm of the absolute value y bounded from 1 to 2. And that's just a definite integral that you can solve, which lands you at an answer of 3 over 2 plus 1/4 natural logarithm of 2. And you can always just remove that absolute value since you already know that it's a positive number, so you could just say natural logarithm of 2. And that is our final answer. Thank you for watching. Today's video is going over surface area, and if you thought arc length was anything close to disk and washer method, this is basically just shell method except one slightly varied step, which is the square root of 1 plus dy over dx squared, or it could be dx over dy squared as well, depending on which you're rotating about. Now the reason this is so similar to shell method is because we are revisiting the 2 pi as well as our radius, which here is x or y, depending on which axis you're rotating about, but this time we are multiplying with the arc length formula, which if you recall over here in my notes is the square root of 1 plus dy over dx squared or dx over dy squared, depending on what your function is. Now, if you ever get confused on which one is your radius for surface area, you don't have to draw the rectangles or anything to remember it. I just think, oh, I see the x-axis, I'm going to multiply it in terms of y. Or I see the y-axis, I'm going to multiply the terms of x. So basically just the opposite of each other. If you see rotate about the x-axis, use the y variable. If you see rotate about the y-axis, use your x. So let's get into some examples. So let's let our first equation be y equals x cubed, bounded by 0 less than or equal to x, less than or equal to 1. And let's rotate it about the x-axis. So let's write down what formula we would use. Of course, we put the 2 pi in front, and then the integral from 0 to 1, which I got from this inequality right here, since this is stating that x equals 0 and x equals 1, which are your bounds, and then y times the square root of 1 plus dy over dx squared dx. And so if you're wondering why I chose this equation in specific, remember what I said earlier, since we are rotating about the x-axis, what we're multiplying by in the front will be the opposite, which is y right here. And how I figured out that we're deriving y is through our original equation y equals x cubed. So of course we don't have all the information we need to plug in, because we do have our y, but we don't have our dy over dx, which is simply just a derivative of our y equals x squared. Because we do have our y, but we don't have our dy over dx, which is simply just a derivative of x cubed, which simply becomes 3x squared. So now we have all of the things we need to plug into this formula, which becomes 2 pi times the integral of x cubed, which I got from this equation because y equals x cubed. So I just substituted in, which also puts all of our terms in x, so it works perfectly, times 1 plus 3x squared dx. Now from here, we could just simplify the inside of the square root, which becomes 1 plus 9x to the fourth, which becomes a simple u substitution. And how I found that out is basically, if I derive this 9x to the fourth, I know that my outcome will have a 3 based on the derivative rules where this will subtract by 1. So it's 4 minus 1, which becomes 3. And I know that that's going to eventually cancel out this x cubed term. So let's let u equal 1 plus 9x to the fourth. Now our du becomes 36x cubed dx, and then our dx will equal du over 36x cubed. So plugging that in gets us the integral of x cubed times the square root of u, and then we'll substitute our dx for du over 36x cubed. We cancel out our x cubes, which simply gets us 2 pi times the integral of the square root of u times du over 36. Now we could just take out a 1 over 36, so let's say 1 over 18 pi, which all I did was simplify this 2 over 36, times the square root of u du. Now I apologize, I did save the bounds for last, which I should have not done. Let me backtrack a little bit. We are bounded from 0 to 1. And remember, when a u substitution occurs, we just plug in our bounds into our equation inside the u substitution, which will simply get us 1 to 10. So our bounds are from 1 to 10. Now our surface area simplifies to 1 over 18 pi times, oh sorry, I meant to put this pi in the numerator. So this is actually pi over 18, or 1 pi over 18, times 2/3 u to the 3/2, bounded from 1 to 10. Now we can remove this constant over here and multiply to the outside, so we end up simplifying to pi over 27 times 10 to the 3/2 minus 10 to the 1, multiplied by 10 to the 3/2 minus 1 to the 3/2, which, if you want to simplify further, our surface area equals pi over 27, 10 times the square root of 10 minus 1. And our first example is finished. I would now like you to do the second one on your own. Now if you notice, we are rotating about the y-axis, and our bounds are x equals 0 as well as x equals 1. So our surface area is going to be 2 pi times the integral from 0 to 1 of x times the square root of 1 plus dx over dy squared dy. And the reason we are deriving x is because our function is an x equals function, so that is why. Now we don't have every detail yet again because we need to solve for the derivative of our x, which is fairly easy because our x equals e to the y, so our dx over dy equals e to the y. So now we have all of our details to plug in. So the integral from 0 to 1 of e to the y, because again we're just plugging in for that x since we know our x, times 1 plus e to the y squared, and then dy. Now this is one of those problems where all you have to do is set up the integral, so if you paused and tried to solve it, I apologize if it took you really long or if you just couldn't figure it out, but I may have forgotten to say set up the integral. So this would be a valid answer when just setting up the integral, but hopefully you get the idea of surface area, and thank you for watching. Today's topic in Calculus 2 is going to be sequences using limits, and we are going to go over 3 techniques. One being L'Hopital's rule, where when you have a limit, you take the derivative of the numerator and the denominator. 2 being Squeeze theorem, where let's say you're comparing g of x, f of x, and h of x, mainly g of x and h of x, and if g of x and h of x equal the same exact thing, then your f of x is also going to equal that thing. For example, if your g of x's limit equals L, and your h of x's limit equals L, then your f of x's limit will equal L. And last but not least, absolute value theorem, where if your limit approaching infinity of the absolute value of a of n approaches 0, then the non-absolute value version would also approach 0, which is just your original function. One thing I forgot to cover is factorials. So basically the gist of it is 5 factorial equals 5 times 4 times 3 times 2 times 1, but you don't need to write the times 1. But you could also write it as 5 factorial equaling 5 times 4 factorial. And that's important if you want to cancel out factorials in the numerator and denominator, which I will exemplify for the 4th problem. And also when you have 1 inside the parentheses, just subtract the inside whole number by 1 when you're multiplying it, same as you're multiplying the whole numbers here, and it will look like this. So let's let our first sequence be a of n equals the natural logarithm of n over the square root of n. And let's set n to go to infinity. So again, we're using limits. So let's let our limit go from n to infinity of our natural logarithm of n over the square root of n. Now, if you notice, if you plug in your n, this becomes infinity over infinity, which is an indeterminate form. So we can use L'Hopital's rule. So taking the derivative of the top and the bottom, the derivative of ln n becomes 1 over n, and then the derivative of the square root of n becomes 1 over 2 times the square root of n. And rearranged, this is basically the same thing as 1 over n times 2 times the square root of n over 1. So then the limit of n to infinity becomes 2 times the square root of n over n. Now you can look at this square root of n to be the same thing as n to the 1/2. So this is the same thing as 2 times n to the 1/2 over n. So if you brought this n down, you could kind of look at it as 2 over n to the 1 minus 1/2, which is just 2 over the square root of n. And let's make sure to put our limit. And when that n becomes a very huge number, that eventually becomes 0. So this converges. I would now like you to do the second problem on your own. So again, our n is approaching infinity, and we have a cosine of n over n squared plus 1, so let's find that limit. Now when we plug in infinity in our cosine of n, what's interesting is the graph will constantly oscillate, meaning we are always bounded by -1 and 1. And because of this bound, we will use squeeze theorem. Now the first thing we need to do is to establish our bounds, which is -1 being less than or equal to cosine of n being less than or equal to +1. Now our next step is to then divide all of our parts by n squared plus 1, since our denominator is n squared plus 1. And then our third step is to find the limit of n approaching infinity for the outer bounds, which is the first and the last bound. So let's set our limit as n approaches the infinity of -1 over n squared plus 1, as well as the limit of n approaching infinity of 1 over n squared plus 1. Now, since our denominators on both get so large, they both approach 0. And notice in our little rules over here, if they approach the same thing, L, which in this case is 0, then our cosine of n, which is in the middle, will also approach 0. So our limit as n approaches infinity of our cosine of n over n squared plus 1 approaches 0, which of course converges. So let's let our third problem be a of n equals -1 to the n over the square root of n. And then let's find it as n approaches infinity. So if you notice, plugging in 1, 2, 3, and 4, and then etc. to your n alternates it from -1 plus 1, -1 plus 1, and it just keeps doing that. So what you're going to want to do when you see an alternating sequence like that is to use an absolute value, which is going to be the absolute value theorem. So let's try to set up our limit as n approaches infinity of -1 to the n over square root of n. Now for absolute value theorem, you just take the absolute value of your entire a of n, which you could basically just simplify as taking the absolute value of the numerator over the absolute value of the denominator, which does get rid of the entire hassle of the -1 to the n, making it just +1, and then over the square root of n. Now this makes everything so much more simpler, as this just approaches 0 when you plug in your n, proving that the limit approaching n over infinity of the absolute value of your a of n is 0. Therefore, the original limit that was set must also be 0. So your final answer is 0, converges. Now last but not least, let's let a of n equal n factorial over n plus 2 factorial. And of course, let's let n approach infinity. Now what's our goal here? Our goal is to try to simplify these factorials so they can cancel out. So we can mainly tamper with our denominator over here, which n plus 2 factorial just equals n plus 2. And again, remember we're subtracting 1 from the whole number. So it's going to be times n plus 1 and then times n factorial. Now if we just substitute that into our denominator here, our a of n equals n factorial over n plus 2 times n plus 1 times n factorial. Now if you notice, our n's cancel out, so we are just left with a of n equals 1 over n plus 2 times n plus 1. So we could then put that in limit form as n approaches infinity and evaluate since our denominator approaches infinity, and then FOIL our denominator, which gets us n squared plus 3n plus 2, which we can then conclude 1 over infinity, which converges to 0. Today's video is going to go over 5 series related topics, which are geometric, divergence test, integral test, telescoping, and approximations. And what you need to know about geometric is that it is a constant ratio r, and with that ratio, if the absolute value of that ratio is less than 1, the series will converge, and if it's greater than 1, it will diverge. So if it does converge, you will use a formula where s equals the first term over 1 minus the ratio. The next test is the divergence test, which is the first test you should do, and it's basically just taking the limit, where if your limit of a sub n is not equal to 0, it will diverge. But if it is equal to 0, you need to do a different test, probably the integral test. Speaking of integral test, we will connect using series with integrals, but when doing this test, you have to state whether it is positive, continuous, and decreasing, which I will show you how to prove. And then once those tests are completed, you have to do an evaluation on an improper integral of your series, where the k is the n from your series, which is shown here. And if your integral converges, your series will converge. But if your integral diverges, your series will diverge. Now, a telescoping series is where most of the terms cancel out from writing the sum, which usually requires a partial fraction decomposition. And an example is 1 over n minus 1 over n plus 1. And so what you would do is you would write out your s of n, which is the summation, and you would write out all of your terms, but then you start to notice that the middle terms will cancel out. So this negative b2, and then this b2 will cancel out, this negative b3, this b3 will cancel out, this negative b4, and this b4 that's going to be eventually in here will cancel out, and you're going to be left with the s of n equals b1 minus bn plus 1. And so lastly, you will take the limit of n approaching infinity of this s of n. And lastly, approximations, where this is typically an integral test for convergence, and you will be given an error tolerance of, for example, less than 0.0001, where the goal is to find how many terms are needed. And all of this will be demonstrated in today's video. Now our first series is going to be the summation of 2 to the power of 2k minus 1 over 9 to the power of k plus 1. And our starting term will be 1, and it is an infinite series. Now we could rewrite this as 2 to the power of 2k times 2 to the power of negative 1, all over 9 to the power of k times 9 to the power of 1. And if you're wondering how I did that, I just raised individual powers to the coefficient. So again, simplified, this becomes 4 to the power of k times 1/2 over 9k times 9. Now we could bring this 2 down, since it is a 1/2, and multiply to the denominator. And all in all, this gets you 1 over 18 when you multiply these two, times 4 to the power of k over 9 to the power of k, which then leads you to 1 over 18 times 4 over 9 to the power of k. Now this doesn't quite follow the form of a r to the n minus 1, so all you have to do is just do 1 over 18 times a 4 over 9 times the same exact 4 over 9, but this time it's going to be raised to the k minus 1. And so this is basically the same exact thing as this over here, but in this case it just more accurately represents this. Now this is identified as our r, which is our ratio, which 4 over 9 is less than 1. And remember, if our absolute value of our ratio is less than 1, our series will converge. So the form of a converged geometric series is that the sum equals a over 1 minus r, which again, our a is our first term. So we will plug that into this equation that we made, where if our k equals 1, this becomes 1 over 18 times 4 over 9 times 1 over 1 minus 4 over 9, which in the very end gets you 2 over 45. So our second problem will be the infinite series of sine of n over n plus 1, starting at the term 1. Now, like I said earlier, something you want to do all the time is a divergence test first before doing anything else, which is basically just taking the limit of your a sub n into infinity, which we are taking that limit of sine of n over n plus 1. But if you notice, it's kind of hard to comprehend doing this to sine itself, so let's try to take the limit of the inside of sine, which is just n over n plus 1. And you can always do L'Hopital's rule, which just ends up being the derivative of the numerator, which is 1, over the derivative of the denominator, which is just 1 plus 0, which eventually becomes 1. So then if you plug that 1 into the sine, you just get sine of 1. And since that does not equal 0, this will diverge. But again, if it did equal 0, you would have to do a different test, like the integral test, which is our number 3. So we are taking the infinite series, starting at 2, of 1 over k times the ln of k. Now let's make our f of x equal our a of n, placing all of our k terms with x and testing our three tests. Is it continuous? Is it positive? Does it decrease? Let's find out. So to prove it's continuous, if you just plug in any value in our bounds, the denominator will never become 0. To prove it's positive, if you plug in our bounds, our x and our ln x will never become less than 0. It will always be greater than 0 because x is positive and our ln x is positive. And finally, to test for decreasing, we can take the derivative of it, but in this case, it's a fraction, so we could just assume that the denominator is always increasing, which if your denominator is always increasing, it will eventually approach a very low number, maybe 0. So now we could turn this series into an improper integral, where you could really just read this as an integral, as the top is infinity and our bottom is just 2, which I kind of said that wrong. This is from 2 to infinity of 1 over x ln of x dx, which, because this is an improper integral, we will plug in a limit as t approaches infinity of our bounds 2 to t of 1 over x ln x. Now when solving for this integral, it's not too complex. It's just a u substitution where our u equals ln of x and our du equals 1 over x dx, which then, if you multiply both sides by x, you get dx equals x du, which, assuming you know how to do a u substitution, you get our limit as t approaches infinity of the integral bounded by ln 2 to ln. And the reason our bounds are different is, again, we performed a u substitution, so make sure you plug our values into that u, or into the x, of 1 over u du. Now this eventually becomes the limit as t approaches infinity of ln, absolute value of u, bounded from ln 2 to ln t. Now this becomes the natural logarithm of ln t minus the natural logarithm of ln 2, which, sorry, I forgot our limit over here. If we plug in our infinity to t, we find out that this just becomes infinity, which of course diverges by the integral test. And make sure to always put that. I forgot to put it in our divergence test, where it just diverges by divergence test. Now let's let our first problem be the infinite series, starting at 1 of 1 over n times n plus 1. And the first thing you notice is you could do a partial fraction decomposition on this a sub n. So this becomes a over n plus b over n plus 1, setting it equal to 1 over n times n plus 1. Now again, if you see a partial fraction decomposition possibility in our a sub n, this calls for a telescoping series. I kind of don't know why I drew a sun. That would be bad. There we go. So let's multiply both sides by n times n plus 1, which eventually gets us a times n plus 1 plus b times n equals 1. Now if you set n equal to 0, you get 1a equals 1, which a becomes 1. And if you plug that a into here, and if you set n equals to negative 1, then you get negative b equals 1. So b equals negative 1. So if you plug this all the way back into our a of n plus b over n plus 1, we get 1 over n plus negative 1 over n plus 1, which you could just simply say 1 over n minus 1 over n plus 1, and then take the partial sum of the infinite series. So if you notice, if you keep plugging in terms like a sub 1 plus a sub 2 plus a sub 3, you get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, etc. Which, again, these middle terms all cancel out, and this negative 1 over 4 cancels out to the next term, which you eventually get led to 1 over n plus 1 minus 1 over n, and then plus that 1 over n minus 1 over n plus 1. Sorry, I meant this was n minus 1. Now eventually these terms cancel out, which these two obviously do, and then this one cancels out inside, and we are left with our outer terms 1 minus 1 over an n plus 1, which we could do a limit of n approaching infinity of 1 minus 1 over n plus 1, which then becomes 1 minus 0, which equals 1. So this series converges to 1 by telescoping. Now last but not least, let's do an approximation problem of an infinite series starting at 1 of 1 over n cubed with error less than 0.0001. Now our r of n, which means our error remainder, is going to be bounded by our improper integral of f of x dx, meaning we have to find an n such that the r of n is less than 0.0001. So let's take our improper integral of n to infinity of 1 over x cubed, which I just translated this 1 over n cubed to an f of x, or x, then dx. Now since this is an improper integral, we'll take our limit as t approaches infinity, replacing the infinity with t, so it's going to be from n to t of 1 over x cubed dx, which then becomes the limit as t approaches infinity of our x to the negative 2 over negative 2 bounded from n to t. Now further evaluating it, our limit as t approaches infinity of t to the negative 2 over negative 2 minus our n to the negative 2 over negative 2. And we could just rewrite that as the limit of t approaches infinity of negative 1 over 2 times t squared minus negative 1 over 2 n squared, which finally, when we plug in our infinity, brings us to 0 plus 1 over 2 n squared. So now let's solve our inequality, since this is going to be less than 0.0001, which is the same as 1 over 2 n squared is less than 1 over 10,000, which is the same, which when we get the reciprocal is the same as 2n squared is greater than 10,000, because since we flipped it, we also flipped the inequality, which becomes n squared is greater than 5,000, which taking that square root eventually gets our n to be greater than 70.7. And with this integer, always round up, even if it was 70.1, into 71 terms, which is our final answer. Thank you for watching.